So in this video we're going to be going over electrolysis, and electrolysis is basically forcing a current through a cell to produce a chemical change that's not spontaneous, and this cell is called an electrolytic cell. So let's look at a picture. So here we have a typical galvanic cell with zinc and copper, and then so the tendency for this redox reaction to occur sets up this potential difference that allows the electrons to flow. But if we put a battery here and the battery sets up its own potential difference in the opposite direction to what's originally there, then it will force the electrons to flow in the opposite direction. So this is an electrolytic cell with two cells. Usually in electrolysis there's only one cell. So if we have a metal being reduced into a solid, then we can use stoichiometry to find out how much metal is produced. Now, if you're not familiar with current, the unit of current is amperes, which is 1 coulomb per second. It's basically a measure of how much current is, or how much charge is passing through a given point per second. So we have copper being plated out by electrolysis of aqueous copper sulfate, and we want to find how much copper is deposited when a current of 100 amperes is passed through 5 liters of a 2 molar solution for 1 hour. So the first step is to write out the half reaction that's taking place. Here, copper is being reduced with 2 electrons to form copper solid. So we start with a current, which is 100 amperes is 100 coulombs per 1 second. And then a time period is 1 hour, which is 3600 seconds. And so we're basically just canceling out all the units until we get to a final goal of grams. So after time, the next step we can do is go to moles of electrons. So in 1 mole of electron, there are Faraday's constant of coulombs, which is 96485. So then our coulombs cancel out. And then we can use the molar ratio that we get from this equation. For every 2 moles of electrons, 1 mole of solid copper is formed. So if we multiply all this out, we'll get how many moles of copper solid is formed from this current. So the last step to get the mass is to just use the molar mass of copper. So if we multiply all this out, we get that 118.55 grams of copper solid are plated out when this 100 ampere current is passed through this solution for 1 hour. Now notice how we didn't use these numbers in our problem. That's because the amount of copper sulfate that you start with does not affect how much plates out, because the rate of plating out is constant. It doesn't matter how much you start with. If you only have this much current and this amount of time, the amount you plate out will always be the same, no matter how much you start with. So let's look at what happens when we pass a current through molten lithium bromide. Now molten means it's in the liquid state, so it's in ions, Li plus and Br minus, but there's no water or anything. So we have 2 platinum electrodes, and we have a battery over here. So the first step is to write out all the possible reactions. So the only possible oxidation reaction is bromine getting oxidized. Lithium can't be oxidized because it's already it's already positive. It can't get any more positive. The only thing that can be oxidized is bromine because it has a negative charge. And then the only thing that can be reduced is lithium because it has a positive charge. So when we have a molten compound, it's easy because there are only one possible anode reaction and only one possible cathode reaction. Now notice how both of these reactions have a negative potential. So this reaction does not occur spontaneously. That's why we need the battery here to produce this change. Now, if we have aqueous lithium bromide, it's a little more complicated because in addition to the lithium and bromine ions, water can also take place in the reaction. So again, we have to list out all the possible reactions. So at the anode, either bromine or water can be oxidized. And at the cathode, either lithium or water can be reduced. So once you list out all the possible reactions, then you have to look at the half reaction potential to determine which one happens. So the reaction with the highest potential will occur. So in the anode, bromine will get oxidized because its potential is less negative than the potential of water being oxidized. And in the cathode, water will get reduced because its potential is much higher than the reduction of lithium. Now, we have to be careful because sometimes just looking at these half reaction potentials does not accurately tell you which reactions occur. An example of this is the electrolysis of aqueous sodium chloride. So the possible anode reactions are chlorine and water. Now, just looking at these potentials, we'd expect water to get oxidized because its potential is less negative than the potential of chlorine. However, in reality, the chlorine will actually be oxidized before water. Now, this phenomenon is called overvoltage, which is basically you need extra voltage for a reaction to occur, like more than just what the half reaction potential tells you. And so water has a higher overvoltage than chlorine, which means in reality we actually need more voltage than this number. Now, basically this is caused by differences in real and ideal conditions.